Hello and welcome YouTube, Mr. Robins back here with yet another brand new exciting video, all math based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. If you step on inside, I was just turning around, I was listening to the screen as I was prepping some of my slides here, and I found out that today, January 31st, is Ernie Banks' birthday, Jackie Robinson's birthday, and Nolan Ryan's birthday. I didn't know that. I had no idea. Who knew? So happy birthday to all of them. Let's go to math. Integrated Math 2 in the Big Ideas Math textbook. Chapter 7 begins, and it's titled Quadrilaterals and Other Polygons. Now, this section 7.1 that we're going to do, and I think it's a smaller chapter. I haven't downloaded all the PDFs right now myself. By the way, if you want to find this PDF, check the description section down below. But I believe the rest of this chapter is more on quadrilaterals. This one is just on any old polygon in general. I got a yawn, so excuse me. Any old polygon in general and finding their angle measures. I mean, there's a lot of stuff with these here, and it brought me back immediately to when I had taught this stuff in the past that I got to grab my calculator probably. There are a lot of bigger numbers we got to add in the hundreds or to get to hundreds, and you don't want to make a mistake. So grab your calculator as well if you want to check this out. Find the PDFs in the description section down below. Find timestamps to the problems you're going to be looking at. I'm going to be beginning with a lecture portion that could take, I don't know. You can find the time slider and see. Sometimes they take about 20 minutes. Let's see what they're going to be talking about here, and let's see if I can follow up with anything with you guys as well on this particular section. And we do all the 52 problems that they also have advertised. So let's see what we got here. We begin with, we will be learning how to use the interior angle measures of polygons and the exterior angle measures of polygons. Now, I'm sure you know what interior angle measures look like, the ones on the inside. You might not know what the exterior angles are just yet. We'll get to those. But we're going to find their sums and all of that. Some core vocabulary we're going to use. The word diagonal. And I know you know the diagonal looks like this, but guess what? This is a diagonal. So they're not all diagonal, so don't think diagonal like that. Equilateral polygon, equiangular polygon. I think we just saw these two words recently as well. Irregular polygon. Some previous words. I don't know when we did use exterior angles apparently at some point. Okay. Polygon, convex, interior angles, exterior angles. You know what? Now that I think about it, I think we might have used it for some triangle things. Not in a lecture, but in some problems if you saw them. Okay, let's see how to use interior angle measures of polygons. Now, in a polygon, two vertices that are endpoints of the same side are called consecutive vertices. So, boom, boom. B and C are consecutive vertices. C and D are consecutive vertices, etc., etc., etc. The diagonal of a polygon is a segment that joins two non-consecutive vertices. So, B and C form to join a side, but B and D form to join a diagonal. You can make a diagonal from B to D. You can make a diagonal from B to E. Heck, I could have made one from C to A, from C to E, from D to A. And I have a star. There it is. So you can join all of those. But for the sake of argument, draw them all from a single one. And we're going to talk more about what we can do with them. But here are two diagonals, BD and BE, among the other diagonals that exist. As you can see, the diagonals from one vertex divide a polygon into triangles. So like I said, if you draw it just from B, all the diagonals, all two of them in this pentagon, this is a five-sided shape, by the way, you make triangles out of it, and unique triangles in the way that the triangles are made from the vertices of the polygon itself. So BCD could be a triangle, BDE is a triangle, BEA is a triangle, all of them vertices of it. This is important. This is important for a formula here. Dividing a polygon with n sides into n minus 2 triangles shows the sum of the measures of the interior angles of a polygon is a multiple of 180 degrees. Here's what they're saying. The interior angle sum of any triangle is 180 degrees. This triangle would have an interior angle sum of 180. This triangle would have an interior angle sum of 180. And this triangle would have an interior angle sum of 180. All of them do. But the fact that these triangles are made up solely of angles of your bigger polygon, like this is one of your angles, this is one of your angles made up from those three, this angle is on its own, this angle is made up of those two, and this angle is made up of those two. The fact that these all have interior angle sums of 180 means that the entire polygon has an interior angle sum of 180 times 3. Now, how many triangles are there? There are always 2 less triangles than there are sides. That's why they said dividing a polygon with n sides into n minus 2 triangles. This is a 5-sided shape, and there are 3 triangles inside of here. There always will be when you draw them in this format. So there's a formula we can make out of that I can find the interior angle sum of a polygon based on the concept of the number of triangles. You don't have to think about it that way, but the formula does that thinking for you. So here's the formula. Polygon interior angles theorem says the sum of the measures of the interior angles in a convex, we'll talk about that, n-gon, like a polygon of n sides, is n minus 2 times 180. In other videos or probably in my math, you'll probably see me write 180 times n minus 2. I'm big on writing just a single number first and then that later. But the number of triangles you'd have in there times the degree amount per triangle that there would be. So measure of all your angles down to the nth angle is exactly that. Pardon me. Once again, this is a six-sided shape, a hexagon, so there would be 4 triangles in here. From this angle, this vertex, I could draw diagonals here, here, and here. 3 diagonals makes 1, 2, 3, 4 triangles, and with all interior angle sum of 180, you could actually get its sum as well. Notice I haven't calculated them yet. We'll save them for later. What's nice about those, I'll just go ahead and say this. Being an old Cool Borders video gamer, Tony Hawk's Pro Skater video gamer, SSX video gamer, I'm very used to hearing half-turn spin amounts. 180, 360, 540, 720, 900, 1080, 1260, 1440, 1620, 1800. I don't think you're going to spin that many times unless it's SSX, but I'm used to hearing those turns from extreme sports. 180 degrees is a half turn. So you'll probably learn your multiples of 180 pretty fast overall from seeing these, but if you've ever played those old video games, I think you'd feel the same on them. All right, let's look at some of the examples and kind of rush through them. They'll do the calculations for us. Find the sum of the measures of the interior angles of the figure. We have a 1, 2, 3, 4, 5, 6, 7, 8-sided shape. 8 sides, also 8 angles. You can count them by the vertices as well. Number of sides is number of vertices. So again, you can do either count. You'd be fine. Anyway, so what they do, if n represents the number of sides, then you plug in 8 for n, 8 minus 2 being 6. 6 times 180 is 1080. Once again, 6 is the number of triangles that exists in there. Not that you have to draw them, but the formula does that for you. 1080 degrees is the interior angle sum of this octagon. Now, it's not a regular octagon, definition vocab word that we'll use later, and I just want to bring that up, guys. It doesn't have to look exactly like a stop sign. It doesn't have to be a perfect 8-sided shape for this to happen, right? It doesn't have to look like, let me pull it up. It doesn't have to look like this to have that interior angle sum. Every 8-sided shape in existence has a 1080 degree interior angle sum. There is not one that doesn't. Not a single one that doesn't. And, these probably have the same angles. Actually, that looks like the 135 degree angles that these ones are. But I was going to say, even if they skew it, remember, once one angle gets bigger, another has to make up by being smaller or something like that. And it can stretch out like that. Whatever. As long as it's 8 sides, you can make the shape. Anyway, I'm extending onto that. They'll probably tell us that. But they never mentioned that it was. 1080 degrees. Which is 3 whole spins. Finding the number of sides of a polygon. Let's go backwards. What if you know the sum of the measures of the angles is 900 degrees? Now let's find the number of sides. So the interior angle sum is 900 degrees. And by the way, whenever I write the formula, I'm used to writing D, the degrees of the interior angle sum like this. So get used to me doing a lot of that. Anyway, my D is 900 this time. Now you solve for it here. Now from here to here, they divided both sides by 180. That was just their go-to. I think I would do the same. They should be divisible by 180, mostly because you're doing it based on, this is going to be an integer number of sides, so it's going to have some sort of 180 degree multiple on it. Anyway, n minus 2 is 5. That means 5 triangles in this figure. There are 2 more sides than there are triangles. Add 2 to both sides. You get n equals 7. A 7-sided polygon, otherwise known as a heptagon. I don't know if they're going to have you name some of the shapes here. I'm going to for you if they don't, or they assume you already know it. But triangle, quadrilateral, pentagon, things like that. It's a heptagon for a 7-sided shape. Corollary to the polygon interior angles theorem, the sum of the measures of the interior angles of a quadrilateral is 360 degrees. So corollary is basically an extension of the interior angles theorem thing that we have to the next basic one. We know triangles add to 180, the next one up, quadrilaterals add to 360. That's a big one to know, especially for this chapter. But it makes sense because like a square has 4 90-degree angles, but all of them have 360 degree sum, even if they're not all 90 degrees each. Find an unknown interior angle measure. So let's say this time you have a shape. You know some of the other angles. It's not a regular polygon, meaning all congruent angles and sides. But you know 3 of the 4, and you're trying to find that 4th one. Well, we know it's a quadrilateral, a 4-sided shape. And a 4-sided shape has an interior angle sum of 360. Without having to do the 180 times n minus 2, which you could, we should probably know that the 360 is 360. I almost want to defer to that knowledge. Anyway, they all have to add to 360. So you make an equation out of it. This is where I would kind of use the calculator sometimes if I have to. X plus 108 plus 121 plus 59, add those up and you get 360. Combine like terms here, and then subtract the 288 from both sides, you get 72. X is 72. That is its value. Here's some notes down below. Let's see what they want to say. In an equilateral polygon, here's the regular. Equilateral polygon, all sides are congruent. That doesn't mean the angles have to be the same. Equiangular polygon, all angles are congruent, not necessarily the sides. I think like that octagon. I think that octagon was equiangular, but it wasn't equilateral and therefore wasn't regular. A regular polygon is a convex polygon. That means the angles all kind of stick inward in that way. And then all sides and angles are congruent, both equiangular and equilateral. Okay, let's go ahead and move forward. Let's find the angle measures in more polygons. A home plate for a baseball field is shown. Is it regular? Explain your reasoning. It's not regular because it doesn't have equal angle measures. Some are 90-degree angles drawn by the right angles and some are not. Anyway, find the measures of angle C and angle E. So here's what you can do on this one. It's a pentagon, 5-sided shape. Use the 180 times n minus 2. 5 minus 2 here is 540. That's the interior angle sum of these 5 angles. They mark these as right angles. And honestly, here's what I would do for these when it comes to solving it. I'd put 90. I can't tell you how many listen, I know that you know it's 90 degrees. I can't tell you how many times students forget to write the 90-degree angle because there's no number there. I'm going to tell you right now that if you ignore me on that statement, you might accidentally do that. Please write the 90. I'll even write the 90, and I don't plan on missing it. And I'm just going to call these ones X. These are unknowns, but they are the same unknown. They're both equal. This is a home plate, man. This is my territory. They're going to be the same. Anyway, 2x's plus 3 90s is 540. 2x plus 270, subtract and divide by 2. You get x equals 135. Each measure of the angle is 135 degrees. Okay. Here's some more stuff. I'll let you play with that. But once again, if these are unknowns, just go ahead and mark them with X. You can see that they're both X's with that. Find their measures. You'd be good. Okay, using exterior angle measures of polygons. This is a unique and interesting thing. First of all, exterior angles, they have them marked. Check out what you have here. 5-sided shape, a pentagon right there. But the exterior angle isn't this entire thing right here. It's not this. No. You take a side and extend it, either set, and then it's just one of the ones that's supplementary to the interior angle here. 3 and 2 and 1. They are just these small angles right here. You can go one of two directions. You could talk about this being 2 or its vertical angle hypotenuse. This one being 2 as well. Those are 2 of the same exterior angle. You only should be listing them once, but you can use either. Either extend that side, take its supplement, or extend this side and take its supplement. Anyway, 5 exterior angles for this polygon. Unlike the sum of the interior angle measures of a convex polygon, the sum of the exterior angle... I can't read this. Hold on. Unlike the sum of the interior angle measures of a convex polygon, the sum of the exterior angle measures does not depend on the number of sides. Remember, as the interior angles, as the polygon number of sides went up, so did the interior angle sum. Think about why that is. Before I keep reading on, let's think about why that is. I'm going to be drawing some of these shapes for you guys. Triangle, square, I'll name them as well. Triangle, square, pentagon, hexagon, heptagon, octagon, nonagon, decagon. Boom, like that. The more shapes, the more sides that you add, kind of the rounder that it gets as a result. You know, like that. The interior angle sum gets bigger. Why? Because you have more angles and those angles get bigger. The triangle has acute angles, then suddenly the square, well, equilateral, suddenly the square has 90-degree angles. Suddenly they're obtuse and more obtuse and most obtuse. They almost look like a circle at some point, right? There are more angles and they are bigger. Now, the real reason why is the triangle thing you saw, but you can tell why they get bigger. Exterior angles, however, the diagram suggests the sum of the measures of the exterior angles, one angle at each vertex of a pentagon, is 360 degrees. In general, this sum is 360 degrees for any convex polygon. When they say in general, they don't mean maybe, sometimes, maybe not. It always is. And they're showing you this right here. If you cut these things out and piece them together, you can see that they complete a full 360-degree circle. Now, why is that the case for exterior angles? Because even though the sides, there are more sides, the angles get smaller as you go. Notice the triangle exterior angle measures, this one, and this one are obtuse. Check what happens in the pentagon with these 5 of them. They suddenly became acute. See, the triangle's angle measures, equilateral at least, these are 120 degrees each. These are, I forget, I was about to say it, now I forget, 72? These are 72 degrees each, I think. 72 degrees each. There are more of them, but they're smaller. Check out how small they are in the decagon, the 10-sided shape. They're really small right here, right? So, now they're 36 degrees here, but there are 10 of them. But they always add to 360. Their sum is 360. It doesn't matter what kind of polygon it is, regular or not, their sum is 360. That's what they're telling you here. Okay, keep moving forward. I like to chat about that stuff a lot. Finding an unknown exterior angle measure, knowing that their sum is 360 for this whatever sided shape, you have these unknowns, put them in your formula there, add it equal to 360. Not 180 times n minus 2, nothing like that. Add it 360, solve for x, you get 68. We'll just kind of leave it at that. That's the example. We'll do our own, of course. Finding angle measures in regular polygons. You can actually find individual angle measures here because they're all the same. So if you find the sum of that specific polygon, divide by the number of sides / angles that there are. That's what they're going to kind of tell you to do. Now, a dodecagon is a polygon with 12-sided shape. It's a 12-sided shape. A decagon is a 10-sided shape. A dodecagon is a 12-sided shape. Find the measure of each interior angle and exterior angle. Okay, the interior angle individual measures comes from knowing its sum. The sum of all 12 angle measures together is 180 times 12 minus 2, which is 1800 degrees. That means with the 12 angles that there are, if you divide 1800 by 12, you get 150. They are each 150 degrees individually. This one is, and so is the other one, so is the other one. We know this because it is a regular dodecagon. All sides, all angles are congruent to each other, and that's going to work out. So they're each 150. The exterior angle thing is a lot easier. You just take 360 divided by 12. 360 is the sum of the of the exterior angles of any polygon, but you divide by the number of angles that there are for 30 degrees on the outside. So this is 30 right here. There's a second way you could do this as well. Remember that the exterior angle is supplementary to its interior angle. If this is 150, this is its supplement 30, 180 minus 150. So the other way to do it is if you already have the interior angle thing, do 180 minus it. And that probably would be easier to find the interior angle. The exterior angle is 360 over 12. Boom. Subtract it from 180. You can get boom. I don't know if they will mention it. They haven't yet. And there's that one. And it looks like they won't. So I might use that every so often, but I think it's more of practicing the stuff you have. Okay. Let's go to the vocabulary and core concept check. Let's look at number 1. Why do vertices connected by a diagonal of a polygon have to be non-consecutive? So based on the drawing, hopefully you know what I meant from the lecture portion. Because if they were consecutive, they would be sides. See, a polygon is formed by sides. If I draw you here a pentagon, here are here A and B and C. From A to C is a diagonal. From A to B is a side. That is a side of your pentagon. B to C is a side of your pentagon. This is a diagonal going across. They have to be non-consecutive. Consecutive ones are sides. Which one doesn't belong? Which sum does not belong with the other 3? Explain your reasoning. Let's mark the first one as A, naturally, and then see if other ones go along with it. The sum of the measures of the interior angles of a quadrilateral. Why notes 360 degrees? Let's see what else they have to talk about. The sum of the measures of the exterior angles of a quadrilateral. That's also 360 degrees. It's always 360 degrees. So those go together, as in they're both 360. Let's see if that's what they're talking about for going together or not. Let's see. The sum of the measures of the interior angles of a pentagon. Ooh, that's 540 degrees. That might be the odd man out. Let's see what they're going to say here. I'm going to guess that's the different one. The sum of the measures of the exterior angles of a pentagon. Yeah, that's still 360. That's still A. See, the my explanation is 3 of them add to 360 and the 4th one does not. Any exterior angle sum is always 360 degrees. Doesn't matter their shape. The quadrilateral is the only one specifically with the interior angle sum of 360 degrees. Pentagon is 180 more. It's an extra triangle in it. Okay, guys, I'm going to go ahead and start on the other problems here. Go ahead and get yourselves ready with however it is you're going to do that. Something was coming into me on the screen over there. Let's go ahead and jump right into it. Problems 3 to 52. You excited? Let's go. Let's do it. Anytime I have to use the calculator, it's going to slow things down, so I apologize. We'll see where we go. Okay. In exercises 3 through 6, find the sum of the measures of the interior angles of the indicated convex polygon. Now, once again, I am going to probably write the formula in my own way. So a nonagon, I guess it sounds like they need you to know what kind of shape that is. That's a 9-sided shape, 9 sides. So n equals 9. Okay, I think later I'm just going to say n equals 9 instead of writing 9 sides. For our formula, d equals 180 times n minus 2. That's how I'm going to use it. Here we're going to be able to say d equals 180 times 9 minus 2. 9 is the number of sides. 9 minus 2 is the number of triangles that exist inside of that guy right there. And 180 times 7, oh gosh, I thought I knew that. 180 times 7 is, let's see, 3 and a half, 1260. See, I know it when I think of like snowboarding. 1260 degrees. Yeah, multiplying it I didn't know, but 7 is 7 half turns, and I know that that's 3 full turns plus another half turn. So that's how I know these things. I'm probably going to calculate them that way, but some of them are probably more than the number of spins I've seen even in a video game, so I got to multiply some of them, I'm sure. All right, a 14 gon. See, they write that instead of the official name. I don't know if there is an official name that's a part of it, and even if they did, they don't expect you to know it. So n equals 14, clearly. So the interior angle sum of this one is going to be 180 times 14 minus 2, which is 180 times 12. 180 times 12, I think is 2160. 2,160 degrees is the interior angle sum of a 14 gon. Number 5. Number 5, we have a 16 gon. Now, as far as my calculations go, hold on a second. Obviously, n equals 16. As far as the 16 gon goes, that's going to be 180 times 16 minus 2, or 180 times 14. As far as, why did my pen thing change? Give me 1 second. That probably changed a little bit ago. I'm only now realizing. 180 times 14. You might not notice the difference in this pen style and this pen style. Now, even if I didn't know what the calculation was, 16-sided shape has 360 degrees more than a 14-sided shape because it's 2 more triangles. So I'm, in my head, going to do 2160 plus 360. Excuse me, that's 2,520. I don't even know if I've seen that number before when it comes to these things and calculating it. So that one's new to me, definitely not on the spin basis. What I do know is it's 360 more than that number, and I believe that number is accurate. Let's keep going. Number 6, 20 gon. 4 more than this one. Maybe I can work off of it like that. Oh, I also know 18 squared, so I can get it off that too. So 20 gon. Helps to know some numbers. N equals 20. So we're going to have to do D equals... And honestly, I wish they did more of the smaller ones. Not because this isn't worth it here. Because they tell you the name and you get to practice the name that way. I don't know. I'm old school like that. They're just saying, oh, we're going to make you write a bigger number this time. See, 18 times 18 is 324. So 180 times 18 is 3,240. There you go, sport. All right, that's numbers 3 through 6 where we found those. Let's keep going. In exercises 7 through 10, the sum of the measures of the interior angles of a convex polygon is given. Classify the polygon by the number of sides. So now we're going to go opposite of what we did before. This is the sum. Let's now find out the number of sides that there were. Use the same formula, but this time we set D equal to 720, the sum, and we try and find N, like this. So 720 being the sum is how many triangles? Divide this by 180. 720 divided by 180 is 4. There are 4 triangles in this shape, 2 less triangles than there are sides. Add 2 to both sides, you get 6. There are 6 sides. It's a 6-sided shape, also known as a hexagon. And if I know the name, I'm going to tell you. I can't remember the name of an 11-sided shape. I'm thinking about it. I'm trying to remember. M-decagon? E-M? I had to look it up. last year. I don't remember. That's probably way wrong too. N-decagon. Oh gosh. Didecagon? I do not remember. We'll see if I run into that one. 1080. 1080 degrees. 3 full turns. It's going to be 6. Excuse me. 6 triangles. 8 sides. Anyway, 1080. I cheated a little bit. So 1080 equals 180 times n minus 2. And you divide that there, you get 6 divided by 1, n minus 2, so n equals 8. 8 sides, otherwise known as an octagon. Like so. Like so, you get an octagon there. Number 9, 2520. Well, we just saw that one on problem 5. I think it's the 16 gon. I think this answer is going to be 16. Let's check this out. 2520 degrees. So set it equal 180 times n minus 2. I'm just going to confirm on the calculator. 2520 divided by 1080. Let's see. I got to turn it on. 2520 divided by 180. Excuse me. 14. Oh, because the answer is 16. Yeah. So 14 equals n minus 2. Add 2 to both sides. N is 16. 16 sides. I do not know the name of the shape. Apparently neither did they, or at least they didn't want to tell us. 16 sides there, and number 10, 3240. Well, that was the other number that we saw, right? So this is going to be, what, a 20-sided shape? But it's going to start with 18. So 3240 equals 180 times n minus 2. Kind of like from problem number 6, I know that this divided by 180 is going to be 18 because square root of 324 is 18. N minus 2, and therefore n is 20 sides. Also don't know the name. Ventagon? I don't know. All right, number 11. Numbers 11 through 14, find the value of x. So this time we have some shapes. I'm just going to go off the shape that's drawn over there, if you don't mind. The copying and pasting is just going to add a little bit. There are a lot of problems with shapes, so doing it each time is just going to add a little bit more time. So given what we have there, though, we want to first find the interior angle sum of our item. Now, all of these are quadrilaterals. So the very first time I do this is the only time I'm going to do it. 180 times 4 minus 2 is 180 times 2, which is 360 degrees. That is the interior angle sum of a quadrilateral. Doesn't matter what kind it is. So, for number 11, I'm going to add x, not the vertex, but the variable, with 100, 130, and 66, and that's going to be equal to 360. Let's solve for x. It's 230, 296. X plus 296 is 360. Subtract 296 from both sides, you get 64. X equals 64. That'll do it. That'll complete that one. Okay, number 12. Same thing. 4-sided shape. Its interior angle sum is 360. Add it with x. Looks like they really want to dig you into the know your quadrilateral business. That's kind of their beginning mark on this stuff. X plus, I want to use my calculator, 236 plus 58 is 294. Oh, it's really close to the last one. I really apologize if I make mistakes on some of these. The fact that I'm setting up the equation for you is probably more for you to say, try it on your own, kids. You got this thing. 66 this time. Let's double check that. 236 plus 50. I think that's 290. Yeah, I think that's good. Number 13. That's 1, 2, 3, 4. Still a 4. So I think these are all quadrilaterals, at least to begin with. Number 13. X plus 154 plus 88 plus 29 equals 360. 154 plus 88 is 242 plus 29 is 271. X plus 271. Subtract 271 from both sides. X equals 89. Now you might be wondering, Mr. Robinson, why are you not putting the degree symbol? You put the degree symbol on the answers to the previous problems. X is already in degrees. There's a degree symbol right there. So if they said find the measure of angle W, I would have said for that one 64 degrees. For this problem, measure of angle M, 89 degrees. So it just depends on the problem and what's being asked in it. Number 14, also a quadrilateral. Let's add x, 92, 68, and 101. And you get 360. 92 plus 68 is 160. Plus 101 is 261. Subtract 261. If this was 89, then this is supposed to be 99. All right. Trusting my own math. That's a scary thing to do, but I believe it. Let's keep moving forward. Numbers 15 through 18 also find the value of x. However, this time it is not a four-sided shape. And is it always the same number of sides? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. No. So they're different at different times. We got to find interior angle sums based on them different ways. I can tell you what I know from some of them once I see them, but we'll still calculate them together. Six-sided shape has 720 degree thing. Okay, so D is 180 times 6 minus 2. Once again, the diagram's over there, so I hope that you're okay with that. So this is the number of sides right there, 6 sides. 180 times 4, which is your 720. 4 half rotations, 2 full rotations, 720 degrees. So we are going to add those together and set it equal to 720. At times, you will see me use the calculator more. This may be one of those times. I'm going to first try it without and see how long it takes. The calculator sometimes takes a little bit a while as well because I'm not punching with my thumbs. I have to click on a mouse here. I don't have to here, but if I want to present something for you, I would. All right, 102. Okay, let's do this. 248. I already regret this. 368. 492. 650. 650. X plus 650. That's probably faster on a calculator. Subtract 650 here and you get 70. 70. I believe it. Listen, they say these things aren't drawn to scale, but I believe they make them to scale, so I believe that that would be a 70-degree angle. If I had something like 120, I'd say, uh-oh, I think I messed up. But there you have it. Or if I got a negative answer, I'd say I messed up. If I don't carry a 1 over somewhere, that absolutely will happen. All right, number 16, we have a 1, 2, 3, 4, 5-sided shape. So this time, 180 times 5 minus 2. We saw this in our very first example, I believe, was 540 degrees, or at least 3 180s. So 540 degrees. So let's add those together. The less angles, the better, especially when it comes to me not using a calculator. Okay. 86 plus 140 is 226. Plus 138 is 364. Plus 59 is 413. No. 423. Right? Uh-oh. I'm going to double check this one. 117. At least it looks like it could be 117. I'm going to I'm going to go with the calculator for 2 reasons. To double check my answer and to see how much faster it goes if I do. All right, let's do this. Let's do 86 plus 140. Let's see. Suddenly this feels slower again. But it's also going to be accurate. 423. Okay, cool. Okay. Let's go. So 117 on that guy. Number 17. This is one of the ones, if you heard me in the notes section of this, I very highly recommend that on a problem with a right angle that you write your 90 degrees right there. If you don't, you might skip it. I promise you might skip it. And just say this plus this plus this plus this plus this equals. Put the 90, you'll remember it more. Okay, let's do 1, 2, 3, 4, 5, 6. It's a 6. Wait, 1, 2, 3, 4, 5. It's a 6-sided shape. So if n equals 6, then D equals 720. Listen, and I'm telling you this right now. If you already used a value before, use it again. Don't recalculate something if you just came off of it. And I'm not saying Because here's the thing, you might have a table of those values, right? Your teacher might have provided you one. You might have written one on your own. I'm not saying refer to that either. I'm saying that if you just came off of one that you used, use it again. I did it for this quadrilateral 360. Let's do it again. Let's not waste time on that. All right, so these are going to add to 720. X plus 121 plus 96. I'm going to try and add on the fly as I do this. So that's 217. This 318. And that's 480. Oh, shoot. I didn't see the 90. Look at that. No, I thought I was done. 480, 570. And that adds to 720. Okay, x plus 570 equals 720. Subtract that and you get x equals 150. Oh, not the degree symbol, but 150. And look, that looks like a 150. It's less than 180. It is convex. It's going to be less than 180, and it looks good. Number 18. More angles and multiple x's. How many sides? You know, sometimes I mess up with the number of sides. Let's count angles. 1, 2. I guess that's an angle. 3, 4, 5, 6, 7, 8. It's an octagon. I don't know if we did the octagon. We might have. I think it was 1080. Excuse me. 180 times 8 minus 2. Yeah. It says 180 times 6, which is 1080. And if you forget, then redo it, right? So here we go. Let's do x plus 143 plus 2x plus 152 plus 116 plus 125 plus 140 plus 139 equals 1080. You might be asking, Mr. Robinson, is there a faster way to do this? No. No. And yeah, I guess use the calculator. I'm going to use the calculator this time. I can't afford messing up for that. But is there a faster way to do it? No, there's not. This is what you do for the problem. So 143 plus 152. Depends on the problem, though. These are all different values. 116 plus 125 plus 140 plus 139. Okay. So that's going to be 815, but there's also x plus 2x. So together that is 3x. And then here, the rest of them is 815. That's 1080. And we're just solving for x. We're not finding the measure of a specific angle. So with this in mind, we're going to get something. I don't know what that is. I think it's 265. 815. It's 265. And then divide by 3. And I don't know what that is either. Oh, I'm a wreck for this. I don't even know if it's a whole number. Nope. 88.3 repeating. Did I do everything right? I hope so. So I'm going to write it as 265 over 3. 265 over 3. If it's not exact, I ain't going to round. I'm going to leave it as an exact. I need to add to 1080, right? So that's good. Was it a 6-sided? Oh, this wasn't a... Oh, 8-sided shape. 1, 2, 3, 4, 5, 6, 7, 8. You know where I slightly do believe this, though, is that answer. I said it was 88.3 repeating. Take a look at the one in the graphing calculator there. 88.3 repeating. One of my angles is 2x. You know what this times 2 is? 176 point whatever. You know what a straight angle is? 180 degrees. This is really, really close to 180, and this looks really, really close to 180. You might have even confused it for a straight line. It's not. It's nearly. It's just a few degrees off. Literally a few degrees off. And I believe the answer. I just want to write the exact one. I want to write the exact one. All right, find the measures of angle x and y. So in these cases, they don't actually present variables. I will write them as long as there's congruency to be had, you know, things like that. So I'm going to put an x here and an x here as variables. I'm also going to, of course, have this 90 right there. Once we find the measures of the angle, once we find x, the measures of the angles will also be the same, at least for these two problems. Looks like for all of them, they're all congruent like that. So let's go ahead. Number 19, I will do, listen, x plus x is 2x, right? So next time I'll write that. But x plus x, oh, hold on. How many things? 1, 2, 3, 4, 5. 540, right? Hold on. N equals 5. Therefore, D equals 540. Okay, so x plus 164 plus 102 plus 90 equals 540. Okay, so that's the 2x right there, right? Next time I'd write 2x if it's just both of them, and I already know that. 164 plus 1 and 2 is 266, plus 90 is 356. So 2x's is 84, 184. 184. So x is 92. 92 degrees looks like it could be. Those are almost right angles, but just a little bit bigger. So if x is 92 degrees, then the measure of angle x equals, same as measure of angle y, of course. They're both the same, and it's 92 degrees, like that. That are the answers. Number 20. Let's find the measures of angle x and y. They look obtuse. I'm expecting something closer to the 135 degree mark. I don't know exactly what it is, but I got another 90 degree angle right there in z. So 90 degrees here, and x, as they are congruent. So this is a 1, 2, 3, 4, 5-sided shape, also 540 degrees. Let's go straight into it. Both x's plus 47 plus 119 plus z90 equals 540. 90 plus 119 is 209, plus 47 is 256. Subtract 256 from both sides, you get another 84, 284. Divide both sides by 2, you get 142. I said close to 135. I was going to push toward 140, but 140, whoops, that's not the answer. I was going to push toward 140, but the answer is 142. Measure of angle x, measure of angle y is 142 degrees. There we go. All right. Number 21. So each problem is going to average a couple minutes when it comes to the calculations we got to do, even if they have a simple structure. 1, 2, 3, 4, 5, 6-sided shape. We saw that was 720 degrees from before. Let's keep it up. Excuse me. D is 720. So this is an x and an x. There's a 90 there. Okay, here we go. Let's go. Both x's plus 159 plus 90 plus 99 plus 171 equals 720. Sorry about the writing. 99 plus 171 is 270. Plus 90 is 360. Plus 159 is 519. This is going to be an odd a decimal. Plus 519 equals 720. Make sure that adds right. Yep. Subtract 519 over, and you get 201. Divide by 2, you get 100.5. It's kind of halfway in there. So measure of angle x, measure of angle y, same thing. I'm not questioning why they're asking us to find both. I'm questioning why they're always the same. And same with 22. Number 22, also congruent x's and y's. Oh yeah, I'm supposed to predict what they are beforehand. I think that's probably closer. I think that's probably closer to 135, more on the side of 130. I'm going to say like 120-ish. 120-ish, but it might be another decimal answer like we just saw before. This time no 90 degree angles, but both a couple x's here. 6 angles means 6 sides, so once again, 720 degrees. Let's just jump right into that. Both x's plus 100 plus 110, that's 210. Plus 149 is 359. Plus 91 is 450. So 450 plus 2x is equals 720. So 2x equals 270. Oh, this is the 135, man. And x equals 135. I didn't know they'd get exact to 135. See, 135 is a special number. It's a 90 degree angle plus another 45, another half of 90. I was trying to get around saying that looks like around that. So measure of angle x and y are both 135 degrees. Okay. All right, that's number 22. Let's keep moving forward. even halfway through. So let's see where we go from that. All right, 23 to 26. We learned in through the lecture portion that the exterior angle sum of any polygon is 360 degrees. We're going to find the value of x given the exterior angle measures we have here. Guys, spoiler alert, 23 to 26, all of exterior angle sums of 360. That's not the answer, but we're always going to add a 360. So, there we go. They added 360. Let's go to war. 65 plus 106 is 171. Plus 78 is 249. So x plus 249 is 360. Let's predict a little more than 90. I'll say around 100. Like, we'll see 96 degrees. 360. Oh, actually, shoot. I should look right from here. Oh, really? Like 110? I'm not good at looking at my numbers. 111. X equals 111? Did I math right? Is that 111? Let me double check that. 65 plus 106 is 171, plus 78 is 249. Yeah, 111, okay. Maybe it's not drawn to scale, or maybe I don't see my scale right. No more predicting. You stop predicting. All right, these add to 360 again, number 24. Two x's there. You see them on the bottom. Two x's plus your 59, 48, 50, 39, and 58. I'm going to try and do something a little tricky here. I'm going to pretend like this is 60 and 50 and 40 and 60. 60 plus 50 is 110. Plus 50 is 160. Plus 40. Wait, did I say 160? Plus 40 is 200. Plus 60 is 260. Minus 136. Did I say 260? I forgot my number. 260 minus 6, 254. I mean, I would do that faster in my head, but I think that's right. Hold on. 60. Yeah, I'm going to go for that. All right, so 2x. See, I just did that in my head like that. 2x equals 106. So x equals 53. Each of them are 53. Those two are congruent there. Number 25. Okay. This one literally has a 2x. It also has a 3x. I'll go ahead and just put them together. 2x, I mean, separately. Literally separately, opposite sides of the equation here. Still equals 360, no change. 2x plus 3x is 5x. And then I got 156, 200, 200. Subtract 200, and you get 160. Divide by 5, you get 32. Okay? And then number 26. Number 26, I got down to the bottom left. I'm starting from there and wrapping my way upward. 2x, 45, 40, x, and 77. Five-sided shape, still a 360 degree exterior angle sum. 2x plus x is 3x. 85 plus 77 is 162. Number of baseball games in a season. One of my favorite numbers of all time. And keep it that way. Do not reduce the number of baseball games in a season, please. 3x equals 198. X equals 66. I think that's 66 there. And it sure looks enough like 66 for me to say I'm going to move on. Okay, in 27 to 30, find the measure of each interior angle and each exterior angle of the indicated regular polygon. So pentagon, listen, we've done the 540 so many times for this one that I'm going to leave it as such. So a pentagon where n equals 5, our interior angle sum is 540 degrees. That's not what they asked for, though. They asked for the measure of each interior angle. I'm going to mark it with I. I is your degree sum divided by your number of sides. That's 108 degrees. Okay? That's how you find that one. This is a regular polygon. They're all going to be equal angle measures. The exterior angle sum can be found one of two ways. 360 divided by 5, which is 72. Or you could have done 180 minus 108, because in any polygon, not regular, not just pentagons, in any polygon, but for this pentagon right here, this is the interior angle measure. This is the exterior angle measure. What do you see about them? They are a linear pair. 72 plus 108, straight angle, 180 degrees. The faster way to do any of these problems, honestly, and I'll do it for some of them, is to find the exterior angle measure first and subtract it from 180. The book didn't tell you that, but you can do it. 18 gon, I don't think we did yet. We did the 16 gon and 20 gon, but let's look at number 28. I want to do it with this one to show you what I'm talking about. And then we can go from there. So 18 gon, we know that means n equals 18. Let's find the exterior angle measure first. Let's do 360, the sum of those divided by 18. That's 20. 20. They're each 20 degrees. The interior angle is 180 minus 20, which is 160. Without doing 180 times 18 minus 2 and then dividing that by 18 to get my 160, I did just that right there. So there are faster measures. It depends on what you're doing. I'm not trying to take shortcuts. This is not a shortcut. This is efficiency. If I needed the sum first, different story. 45 gon. Listen, I'm going to do this as long as I know the division with 360, and I know this division with 360. Exterior angle measure is 360 over 45, which is 8. There are 8. Remember, this is a 45-sided shape. The exterior angle measures are tiny. This is 8 degrees here. So the interior angle measures of any of these is the supplementary angle pair with this, and this is 172 degrees. These are big angles in the interior this way. Yeah, that's what it is. Number 30. 90 gon. 90 gon. A 90 gon. 90-sided shape. It might as well be a circle. I'm just going to say that. That's why these things are getting so slim. What's 360 divided by 90? 4. 4 degrees for each exterior angle measure. Interior is 180 minus 4, which is 176. We saw just how straight a 176 point whatever degree angle measure was right here. This is how, we have 90 of these, but this is how wide that angle is, how obtuse it is, how straight it is. It might as well be a circle. I could tell you this is a 90 gon, and you wouldn't know the difference. You wouldn't know if this was a circle or not. This is just a tool that's drawn a line. Kind of cool. All right. Let's keep going forward. Error analysis. In 31 and 32, describe and correct the error in finding the measure of one exterior angle of a regular pentagon. Now, I don't know. Listen, they never told you about the supplement thing, so I doubt they're going to bring it up here, and I'm not going to correct it in a different way, so I'll correct it their way if they ever need something like that. Exterior angle measure of a regular pentagon? Well, they found the interior angle measure. So they found the interior angle measure. So they did the 180 times n minus 2 thing. That's the number of triangles inside of the thing. Angle measure. An exterior angle measure takes the exterior angle sum, 360, always 360, and takes it and divides it by the number of sides. Okay, so let's correct it. They asked us to. Well, we already found this one, didn't we? One exterior. Oh, okay, we already did that. So E is going to take 360 and divide by 5. Oh, wait. Yeah, okay, I'm sorry. Never mind. 360 by 5 is 72. Okay. Yeah. There it is. Okay. We did that twice now. I don't know why number 27. I don't know why they had us do that twice. They should have done it to a hexagon or something different. Okay. Number 32. There are a total of 10 exterior angles, 2 at each vertex. So the measure of one exterior angle is 360 divided by 10 is 36. 10 exterior angles, 2 at each vertex. What? Oh, 2 at each. Oh. Okay, here's what they're saying. I forgot. They're talking about pentagons too. I just thought about that a second ago. Okay, in a pentagon, there should be 5 exterior angles. 1, 2, 3, 4, 5. How did I know to extend these directions and not the other directions? You could have done either, but you don't do both. 6, 7, 8, 9, 10. This is what they're doing. They're taking what should have been just a single exterior angle measure at each of these here. Did I do that right? Whoops, I didn't do this one right. They looked at these ones. Now remember, listen, these angles mean absolutely nothing, but they're talking about these here, and then they said, let's double it up here. So they said, there are 10, I just did it again. They just said there are 10 exterior angles for a pentagon. Like that. There are 5. You don't double up each. There's only one exterior angle per vertex. They thought there were 2 exterior angles per vertex instead of just 1. Now they said correct the error. I would get the same answer again of 72 degrees. So I'll do it again. 360. This is the third time in 6 problems that I'm giving the same answer because they said correct it. So E is 360 divided by 5, which is 72 degrees. If you haven't found out an exterior angle an exterior angle measure of a regular pentagon is 72 degrees yet, then you just weren't watching. All right, number 33, modeling with mathematics. The base of a jewelry box is shaped like a regular hexagon. What is the measure of each interior angle of the jewelry box base? Oh, here's a hexagon. So it's a regular hexagon. So regular hexagon, all sides, all angles congruent. So n equals 6. Each interior angle, again, you can do one of 2 ways. I'll show you both. You can either do let's do D first. D, the interior angle sum, is 180 times n minus 2, 6 minus 2, which is 180 times 4, which is 720. Boom. And then you find the each interior angle measure. You do 720 divided by 6, which is 120. That's option number 1. Option number 2 is you find the exterior angle, you find the measure of one exterior angle. You know the sum is 360. Divide that by 6 and you get 60 degrees. And then I is 180 minus that 60 because it's subment, which is 120. I would argue the second one is faster. Which is weird. I'm not saying I didn't grow up going this way. I don't often just approach it that way, and it generally is faster. The only reason why it might not be faster is because I know the interior angle sum of hexagon as 720, and you might not. I mean, we've done it a couple times now, so maybe you do. If I find another one that's faster like that, I will, and I'll say, okay, this time it was faster, because I might not know the exterior angle measure then. All right, number 34, modeling with mathematics. The floor of the gazebo is shaped like a regular decagon. That's a 10-sided shape. Regular decagon. That's where n equals 10. Find the measure of each interior angle of the regular decagon, then find the measure of each exterior angle. It did say find one first, then find the other, so I will follow what they want me to do this time. Okay, if you want the I all in one formula here, you got to take the interior angle sum and divide it by the number of sides, which means you do 180 times the 10 minus 2, and you divide it all by 10. See, there are a bunch of different ways you can go about writing this stuff and how you want to combine them. If that becomes way too complicated, don't do that. I don't know if I generally do. I probably don't. But 180 times 8 over 10, you know why I do like this way? Whoops. You know why I do like this way? Instead of doing 180 times 8 first, I can do 180 divided by 10 first. 180 divided by 10 is 18. And 18 times 8, I wish I knew what that was. That would have helped me, is 144. Really? There are a lot of things. 16 times 9 is also 144. I'm surprised. 144 degrees. That's the measure of each interior angle. Find the measure of each exterior angle. I got one of two options. I can either do 360 divided by 18. Excuse me, not 18. 10. 360 divided by 10, which is 36 degrees. Or 180 minus 144, which is 36 degrees. Arguably, because that was easy division, this was an easier way to go about it. You don't always do supplements. They did say find the exterior angle second. I hope they didn't for the other problems before that, because then no, they didn't. So I did it the way that I did it. All right, writing a formula, number 35. Write a formula to find the number of sides n in a regular polygon given that the measure of one interior angle is x degrees. 35. Write a formula to find the number of sides. So, okay. The number of sides is also the same as the number of angles. Keep that in mind. It says one interior angle is x degrees. I'm going to, just to give you the indicator of kind of what's going on, let's say I had a shape that looked like this. Okay, all those sides, all those angles, each of them is x degrees, and there are n sides. X degrees and n sides means the total sum, d, is going to be x times n degrees. You're going to multiply those things together, right? Because there are n amounts of those x's, or nx. I don't know which way they kind of want to put that. Maybe nx. N times x degrees. Now, what do we do with that? Write a formula, find the number of sides. But to find the number. Okay, so if this is the degree amount there, then remember d is 180 times n minus 2. So n times x equals 180 times n minus 2. Now, n may be the number of sides, but n is also the number of sides here. So now we got to get that n by itself. Oh, shoot. Do we get this n by itself and use that n? No, I gotta keep going. Here's what I'm going to do. I'm going to distribute 180 this time. Distribute 180. N times x equals, I don't know if I had to do all that. I could have done the supplement of this x and said 360. There are probably a lot of ways I could have done this. 180 times n minus 360. This might be weird if you don't know what I'm doing here, if this seems a little too foreign. I'm going to subtract 180n to both sides. Basically, I want to get all terms with n on the same side of the equation. Oh, you know what? I'd rather have my 360 positive. Do you mind if I change that? I'm going to add 360 over and subtract the nx over. So 360 equals 180n minus nx. And I'm going to factor n out, and you get 180 minus x. Therefore, n equals 360 over 180 minus x. That's my answer. I want to see if that kind of works. Let's see, what's the next that I know well? An equilateral, well, no, that's too obvious. Let's do a pentagon. Oh, no, you know what? This totally works. Not only does it totally work, the exterior angle thing would have been so much better for this. The exterior angle one would have been this. If this is x degrees, then the exterior angle right here is 180 minus x. Right? So that's 180 minus x. Now, the number of sides in an exterior angle, the Number of sides is irrelevant in an exterior angle sum, but if I multiply all these by the number of n times 180 minus x, I get 360 because the sum's always 360. 180 minus x times n. So if I divide both sides by 180 minus x, that's what I get, 360 over 180 minus x. Once again, the supplement portion of this totally prevails. I think they're not expecting you to know that information at this point because they never taught you. That was a lot faster than this, but it still got me there. All right, that is number 35. Let's go to number 36, writing a formula. Write a formula to find the number of sides n in a regular polygon given the measure of one exterior angle is x degrees. So this is like, it's a lot faster. So 36 here. Again, the exterior angle is x degrees. How did I write this before? What was I doing at the beginning of the problem? X degrees and n sides. I'll just say exterior angle. Oh, E. E equals, I should have said I before. E equals x degrees. The number of sides n. When you multiply x, the exterior angle thing, by the number of sides, you get 360, the exterior angle sum. When I divide both sides here, you get 360 over x. So if each exterior angle is 360 over the number of sides, then the number of sides is 360 over each exterior angle in a regular polygon. I get it. It works. All right, number 37 and to 40. Find the number of sides for the regular polygon described. Oh, let's use our formulas. So let me write them. Well, here's one of them. So for interior, given an interior angle, because otherwise I was going to go, let's see, we do this, we do that. It was n equals 360 over 180 minus. Now I put x, because they said x. I was going to say, let's put I. But okay, so they said x. That's fine. And then here's the exterior one. Whoops. The exterior angle one. Okay. Each interior angle has a measure of 156 degrees. So let's say n, hold on. I, or x. X equals, I kind of want to say I. I know they said x, but now that I'm writing it as a formula, let's call it I. If I equals 156 degrees, then n equals 360 over 180 minus 156. This totally makes sense when you think about supplements of these things and you know what you're kind of doing with those. I think that's 15. It's not 15 degrees. This is the number of sides that you have. So there are 15 sides when each of them is 156 degrees. Wow, yeah. I like that they had us do a formula beforehand. They didn't tell us to use it, but you got to think that you probably should. Number 38. I equals 165 degrees. So now n is, oh, my eye's hanging. It's kind of like the one from Chicka Chicka Boom Boom. 360 over 180 minus 165. Which is, now I would have done this kind of thing even if I didn't have this formula because, oh, is this 24? 24 sides. Because the other one was, yeah, okay, they're doing this. What was I just saying? I would have done this way anyway. I would have said, well, the supplement is 180 minus this, and think about it in terms of E. Yeah, I would have done that for sure. All right, each exterior angle measure has a measure of 9 degrees. This is going to be a lot of sides. So E equals 9 degrees. So this is just going to be 360 over 9, which is 40 sides. Right? Because if I did 360 over 40, I'd get 9 degrees per exterior angle there. And number 40, I like the problems are fast. Number 40, each exterior angle measure is 6 degrees. So E equals 6 degrees. And then n is 360 over 6, which is 60 sides. One of those almost might as well be a circle things, kind of like the 90 90-sided one. That was quite a bit. Number 41, drawing conclusions. Which of the following angle measures are possible interior angle measures of a regular polygon? Explain your reasoning. Select all that apply. Honestly, I think I'm still using this formula. I'm almost out of water. I have like a droplet left. I might need to go back and get them. So let's check on them. 162 degrees. These are literally parts. Does this do it? Here's what you want to try and do. Let's use the formula we had before. This is interior. Let's use this formula we're doing, 360 over 180 minus whatever. So n equals 360 over 180 minus 162. That's 360 over 118, which is 20. Now, yes, it would have 20 sides. So yes. Now, what would make it a no? What would make it a no is if your number is not divisible by if your 360 is not divisible by your number, by its supplement, if you will. As I look at all of these, I'll tell you which ones are which. I don't think C is going to work, and I don't think D is going to work. I don't think C or D are going to work. B, I think B is going to work. 171 degrees. N equals 360. Oh, I'm sorry. I have to do, yeah, I do think it's going to work. 180 minus 171, which is 360 over 9, which is 40 sides. Yes. Now it's saying explain why. The fact that I'm getting a integer value means that's why. You cannot have a decimal number of sides for something. That's not how that thing works. So part C, I think we're going to notice a crack in the armor here. Remember, these are all about interior, these are all about regular polygons. So each interior angle measure, you can't have them do each 75 degrees here. And these are pretty non-standard. I don't know bigger ones like this off the top of my head. I've never really seen them for this number of sides. So whether I would have expected an answer or not is not something in the cards. 180 minus 75 is 105 degrees. I know that a pentagon's 108. I know that a square is 90, as far as regular ones go. There is no 105. 360 over 105. Not integer. So no. I don't care what it is. It's 3 point something. It's not an integer. Part D, I think the same thing. 40 degrees. No, yeah. The smallest one is 60 degrees for a 3-set for an equilateral triangle. So this is definitely not going to work. 360 over 180 minus 40. 360 over 140 equal, it's not that it doesn't equal not an integer, it equals not an integer, so no. Once again, it's like that thing, you know those YouTube comments or whatever, those comment things that you kids put all the time where it's like no one, literally no one, and puts a blank, and then like everyone or this person, blah, blah, blah. I hate that. It doesn't make sense. Literally no one said nothing. Okay, well that's... No. Literally everyone said nothing. Right? It's not no one. Anyway. I'm ranting about you kids. You kids and your funny stuff. Oh, what is this? Oh my gosh, I don't even know. The polygon interior angles theorem states the sum of the... Okay, so there's our formula. Write a paragraph proof of this theorem for the case when n equals 5. Okay. Oh, do they have a proof? I mean, they did the diagonal thing. Okay, I'll just do the diagonal thing because that's how I prove it. Okay. In a 5-sided shape, I gotta type this right. In a 5-sided shape, such as also known as a pentagon, there are 3 diagonals that can be drawn from one vertex, from a single vertex, to its non-consecutive sides, vertices. Consecutive vertices. No, there are 2 diagonals that can be drawn. I should probably draw this. Not 3. I'm going to go back and erase that. But there are 2. So from this vertex, I can draw one here and here. This is kind of like the proof that they had before, only it's specific for 5, and we're going to do it in paragraph format. So boom and boom, right? Kind of looks like that. Okay, there are 2 diagonals that can be drawn. But it leads to how many triangles? 3. 3 triangles. 1, 2, 3. Which constructs 3 triangles overall, each of which have an interior angle sum of 180 degrees. Because there are 2 less triangles than there are sides, we can calculate its interior angle sum as 2 less than its number of sides, or 2 less than its number of sides times 180 degrees. 180, sorry, I'm trying to use an alt code. 180 degrees, or 5 minus 2 times 180. Like that. Equals, oh my gosh, equals 540 degrees. I think that's kind of how I want to do that. 540 degrees. Okay, cool. I guess that's a paragraph proof. I think that's kind of what they want. That's part A, though. That's a paragraph, all right. All right, part B. You proved statements using mathematical induction on page 402. I did? When was page 402? This is page 409. I never looked at page 402. I don't know what page 402 is. I forget. I know what math induction is. I don't know if I know all the steps. I might have to look at it. Prove this theorem for n is greater than or equal to 3 using mathematical induction in the figure shown. Oh, I'm not good at math induction. First, you assume that it works for k, and then you show that it works for k plus 1. Oh, first you assume that it works when n equals, see, the lowest n can be is 3. So let's see if I remember math induction. Generally, you have to first assume it works for n equals 1. So our formula, this theorem, so the formula is d equals, I write it this way, 180 times n minus 2. So first, I don't have all the thing, I don't even have the page on here, so I can't use that. But I'll write it in my own way. First, we show this works for the initial value. We show this works for n equals 3. Okay, first we show it works for n equals 3. I don't know what I'm supposed to do in the diagram, by the way. I'm not really paying attention to it. Oh, hold on. I'm gonna fill up this water. Give me 1 second. I'm gonna go fill this up. Okay, I'm back. All right, first we show this works for n equals 3. Now, as I was coming back and looking at this, it looks like it said use the diagram, the figure shown. So I'm actually not supposed to use the formula so much. I mean, the formula exists, but the diagram is the thing we want to use. So to work for n equals 3, we need to have like an a sub 1, a sub 2, a sub 3 thing going. So you're literally going to first start with a triangle. Excuse me. And I don't know if we're supposed to actually write the whole first we do. I don't know, but I'm going to go and do it. So let's start with just something like that, where we have a sub 1, a sub 2, and a sub 3. For this to work, we will draw all diagonals we can to non-consecutive sides from one vertex. I can't draw any of them. There aren't any. They're all consecutive sides. A sub 1 is a consecutive vertex with a sub 2, and it's with a sub 3 and all of them, so you can't do anything with that. There's just a single 180 degree one, so D equals 180, which seems to match with 180 times 3 minus 2. And I think maybe that's what we're supposed to do, equals 180 times 3 minus 2, just to kind of show that it's there. Like that. Cool. So they're both the same, right? So maybe I use the formula to tie it in with the same thing as the drawing. Maybe? You multiply by the number of triangles. How about that? Multiply by the number of triangles that there are. Now we show that it works. Now show it works. I forget if I'm supposed to write that or I just teach people that. No, now show it works for, sorry about my handwriting, for n equals k. So this is now with k numbers of sides. This is where this diagram kind of kicks in. I'm just going to kind of, I don't know if I'm supposed to copy and paste it, but the concept is in play. Not for k plus 1 just yet. So maybe I don't really look at the k plus 1 yet. Maybe there's a way I can kind of hide that one. But I'm just at that set leading up to it. Now, before a sub k, there's a sub k minus 1, if you will. So it kind of still uses that one before it. Let me erase what's there. I can paste the other one in after. So this isn't just a 1, 2, 3, 4, 5-sided shape. This is a general, see that kind of dot, dot, dot you have here? There are just so many. This could be a sub 4, a sub 5, a sub 6, a sub 40, and then 41 and 42. So when it comes to triangles, you first got to draw diagonals. Do it from the vertex a sub 1 and just start drawing diagonals all throughout. There aren't only 2 of them. How many are there? There are as many diagonals as there are sides, minus 1 here and 1 here. A sub 1 is 2 consecutive vertices here and here. So the number of diagonals is k minus 2. So yes, I guess you're not really using the formula, but for all these, for all these 180s that there are, 180, 180, 180, remember there aren't just 3 of them. There are k minus 2 of them. D is 180 times k minus 2. K isn't the number of sides. Well, k is the number of sides. K minus 2 is the number of triangles there are. Wait. Yeah, wait. No, hold on a second. Let me think about that. A sub 1, A sub 2. Blah, blah, blah. Is that right? K minus 2 is the number of triangles there are. But what did I say before? I said 2 diagonals for a 1, 2, 3, 4, 5, 6. Okay, there are k minus 2 diagonals. Okay, there was something I said wrong, but something I'm doing correctly now here with a k-sided shape. Yes. And I guess that's it. Degrees. I'm not going to distribute or anything like that. That's what that is. Now show it works, again, I don't know if I'm doing this part right, for n equals k plus 1. Math induction is kind of strange. It's a way of proving things. It's a way of proving that something should continue on forward, that it works for an initial step, it works for a step of any such value within a formula, and it can do it for the one after that as well. In that case, you could then continue forward for any such value with that in mind, given the initial. So now that we're doing that, you can see the diagonals that are here that go to all those except for the consecutive vertices right there. So with the 180, etc. So now the number of triangles that there are goes to k plus 1 minus 2 triangles. So it is D is 180 times k plus 1 minus 2, or 180 times k minus 1. Now, I don't know where you prove statements using math induction, prove this theorem for n is greater than or equal to 3 using maximum figures. I want to see how me writing that allows you to know that it worked. I know there's a k minus 1 right here, but the fact that I wrote this doesn't say anything about it, if that makes sense. What does me having that say k minus 1 say, therefore this is good? That's the only question I got to think of. The only thing I can think of is that I know the actual formula itself. But I'm using it for a different reason. So I guess yay. I guess for now, yay, because I didn't use the formula. I used the concept for number of triangles there are. I'm just going to go ahead and leave it at that. I'm not a big math induction guy, and I don't have the page that it's on. All right, let's just move on from that. Let's look at number 3, and let's prove a corollary. Write a paragraph proof of the corollary to the polygon interior angles theorem. What was the 360 degree one? It was the interior angle sum of a quadrilateral 360 degrees. Paragraph proof? Well, we did the Pentagon one. So honestly, listen, guys, I'm going to copy and paste the Pentagon one because it was the same kind of thing. It was totally the same kind of thing. That was even more sides. So let's see if this works. In a quadrilateral, 4 sides, there's one diagonal that can be drawn from the vertex to its non-consecutive vertex. There's only one, which constructs 2 triangles overall, each of which have an interior angle sum of 180. Because there are 2 less triangles than there are sides, we can calculate this interior angle sum as 2 less than the number of sides times 180, or 4 minus 2 times 180, or 360. I mean, it's still the same kind of bit here. So once again, you can only, let me draw that. So I have a quadrilateral, and I'll go back up, don't worry. But I have a quadrilateral of any kind of look like this. 1, 2, 3, 4, boom. Almost like a trapezoid, something we're going to learn later in this chapter. And if I draw a diagonal through there, I've constructed 2 triangles, each with an interior angle sum of 180. Therefore, you have 360 degrees. You can only draw one of them to construct angles from the interior angles, such as that, and make that happen. So there's that. You can pause this if you want to take a look at it again still and kind of type it out. It seems like maybe I didn't do the first one right, but this seems to work just fine here. All right, let's keep going. Let's move to number 44. Making an argument. Your friend claims that to find the interior angle measures of a regular polygon, you do not have to use the polygon interior angles. I've been talking about this the entire time. You do not have to use the polygon interior angles theorem. You can instead use the polygon exterior angles theorem and then the linear pair postulate. Is your friend correct? Explain your reasoning. Yes. So I'm not saying that, they should have taught the other one before or whatever, but they never did and saved it for question 44. Yes. Your friend is not only correct, but he or she or they are wise. Is wise. There are several instances where this can be beneficial. I should just say this out loud. They're saying explain why it's correct. But this can basically be beneficial because I think it'll save time. Why is it correct? Well, we looked at the thing before, but basically, here, I'm going to take out this part. Interior and exterior angles are a linear pair because an exterior angle is the angle made from the extension of a side from your polygon. So that's where you can have those things work together. Now, the polygon exterior angles theorem helps you. This is why it's beneficial. The polygon exterior angle sum is always 360 degrees. That doesn't change. I don't care if you have 1,000 sides. The exterior angle sum is always 360. So I'm going to put that. This is beneficial because the exterior angle sum is always 360 degrees. Not 380, not 370, not 350 degrees. Whereas the interior angle sum would have to be calculated. Now, after that, you just have to divide by the thing. Here, you have to subtract from 180, but I think I'd rather subtract, 48 from 180 rather than do 180 times 48 minus 2, or, whatever the number would be minus 2, right? So it just depends. Okay, in an equilateral hexagon, doesn't say regular, it says equilateral. Hold on. That means all sides equal, not necessarily all angles. 4 of the exterior angles each have a measure of x degrees. The other 2 exterior angles each have a measure of twice the sum of x and 48. Find the measure of each exterior angle. Okay. Although it is equilateral, not necessarily equiangular, and it's not equiangular. We can tell that, probably isn't. I'm going to go ahead and still draw it like that just so I have one. It says twice the sum of x and 48. Here is twice the sum of x and 48. The 2 exterior angles each have this measure. So not in total, but each of them. So it's like that. Now the interior angle sum for a 6-sided shape is 720 degrees. We've used that several times. I have 4x's plus 2 of these, 2 times 2x plus 48. That's going to be 4, right? 4. So hopefully that works. So 4x, oh, this equals 720. 4x plus, I'm distributing, 192 equals 720, or 8x equals 528. Divide by 8, 480 is 60, 66. 66. I'll still say degrees. The only reason is because this doesn't say degrees in it. So I'm going to go ahead and do that. So 66 degrees, find the measure of each. Oh, exterior angle. They said exterior angles. Okay. I don't have to do much different than that anyway. I just got to change the 720 into a 360. Sorry about that. I heard interior angles, and I got to change my drawing. Whoops. Let's do that. Sorry about that. Let's see. Okay. Boom, 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 boom. Okay. So I got to do... Okay, so it's out there. Okay, so it equals 360. Sorry about this. My bad. 360. Okay. Doesn't matter if it's a six-sided shape or not, just except for labeling all the ones that are there. 360. Okay. 192. So that is going to change to 68. Ooh, not a clean number. So x is going to be 5. Oh, why is this taking so long? What's 8.5. 8.5. And I'm still going to put degrees there. So I hope I still did that right. For the exterior angles, each have a measure of x degrees. The other two have a measure of twice. Yeah, I'm going to go with that. All right, 8.5 degree. Excuse me. 8.5 degrees for x. Now 2 times x plus 48. I forgot. Equals 2 times. See, that's when I caught it. 2 times 56.5, which is 113 each. So each for that, each for that. So let's see if that works, because that actually doesn't sound like that works at all. I might have messed something up somewhere. I'm gonna go back and do some of this math. My bad. Oh, it's not 68, it's 168. Shoot. Sorry, guys. I'm very slow to the punch here. Let's do that again. This is why I'm double checking all this. 21 degrees each here. 21 plus 48. See, this is why you need a calculator. 69. And therefore 138. Okay, let's see if that works. For all the things, 138 times 2 is 276. So these two angles alone are 276. The exteriors are 276 degrees. Those are big exterior angle measures. Those are really big. Okay. 276 degrees. Oh, it's a concave polygon. 21. 4 of the 21s is 84. 276 plus 84 is 360. Okay, that's better. That works out. All right, number 46. For a concave polygon, yeah, that's what this last one. Is it true at least one of the interior angle measures must be greater than 180 degrees? If not, give an example. If so, explain your reasoning. So a convex polygon, by the way, are the ones that we've been looking at. That's a circle. Here's a convex polygon right there. All right. A concave polygon would be something where something would like go inward instead. So this is a concave polygon because of that angle that's going up. Is it true at least one of the interior angle measures must be greater than 180? If not, give an example. So explain your... I think it's supposed to be. I think that's the intent, unless I don't know. Oh, they have some below. I totally didn't see that. Yeah, I think that's supposed to be the case. Sorry if I'm misguided in that. I think that's the whole idea of it. So is it true at least one? It says thought-provoking. I must be missing something if they're talking about that. Oh. Yeah, I think so. Yes. So, yes, because that's its definition. I don't really know where to go with that answer. Let me think about that. I don't know where to go with that answer here. I'm just saying, like, that's the definition. I don't know. That's I don't know. That's just how that thing works. So yes, because by definition, one of the angles would. I mean, the whole concave aspect is that one of the angles kind of has that cave in kind of thing. One of the angles would cave in to an angle that's greater than 180 degrees, but less than 360 degrees. I don't know what the question's asking. Maybe you're not supposed to know what a concave polygon is yet. That might be the idea behind it. So, okay. That's part of it, I guess. But yes. Number 47. Write an expression to find the sum of the measures of the interior angles for a concave polygon. Explain your reasoning. For these ones, or what? Okay, let me copy and paste. Well, let me just draw on them. It's still the same interior angle sum. It doesn't matter what kind of thing you have. This is a quadrilateral, so I draw a diagonal right here, and then you still have two triangles. 1, 2. This is a 1, 2, 3, 4, 5 sided shape, but this is the non-consecutive sides in a pentagon. It still has that same 180 times n minus 2. From here, I have diagonals here, here, and here. It's a 1, 2, 3, 4, 5, 6 sided shape, 4 triangles, and in this one, I have 1, 2, 3, 4 of those. So 1, 2, 3, 4, 5 triangles in a 7-sided shape. It's still the same thing. I mean, so what I'm drawing there is kind of my explanation. Write an expression to find the sum. It's still 180 times n minus 2. Still 2 less triangles than there are sides. Just because something is a concave polygon doesn't mean that it doesn't still have the same number of non-consecutive vertices. Okay, number 48. Almost done here. Unless it's like the last problems take 20 minutes each. Number 48. Polygon ABCDEFGH is a regular octagon. We get to draw one of those. I'm going to draw it a lot thinner. Bigger, but thinner this time. I have no idea what we're about to do with it yet, though. Alright, there's my regular octagon. Let's label it. And they did call it regular. It's a regular guy. It's a stop sign. Suppose sides AB and CD are extended to meet at point P. Oh, then I need more room. So let's extend these two sides here like this and like this. And they meet at point P. Okay. Find measure of angle BPC. Looks like a 90-degree angle, but we'll see. Explain your reasoning. Include a diagram with your answer. I will. Okay, here. Okay, I already know more things than. I mean, the answer is going to be 90. Not because it looks it, because I know some more things. The interior angle sum of an octagon is 180 times 8 minus 2, or 180 times 6, which is 900. Okay? Oh, excuse me, not 900, 1080. 1080. An interior angle measure, and you know what, I probably shouldn't have even said all that. Let's just do the exterior angle. And I was going to get to the exterior, but I was going to satisfy their needs, but I forgot. We just extended sides, which means we have exterior angles Here's an exterior angle. Here's an exterior angle. Let's go straight into it. An exterior angle of a regular polygon is 360 in this case minus 8, or divided by 8, which is 45. I'm going straight into it. These are each 45 degrees. This is the third angle of a triangle. So measure of angle P is 180 minus both of those E's, which is 180 minus 45. 2 times 45. 2 times 45, which is 180 minus 90, which is 90 degrees. Anyway, what I was going to do first was show you that this is 135 degrees, and then do 180 minus 135 to get the 45 and stuff like that. But I just realized that those are exterior angles, so I don't have to do that. I wanted to satisfy their needs, but I think them saying the extended side thing satisfies their needs about the exterior angle part, so that's good. Cool problem. All right, number 49. Ooh, 4 parts. I wasn't excited. I was surprised. The formula for the measure of each interior angle in a regular polygon can be written in function notation. Write a function h of n where n is the number of sides in a regular polygon and h of n is the measure of any interior angle in the regular polygon. I kind of did that before. I didn't know that they were actually going to do that. So let's break this down in a couple ways here. N is the number of sides, all that stuff. So remember, I was calling it I before. So now it's h of n. Remember, d is 180 times n minus 2. However, h of n is taking your interior angle sum and dividing it by n, the number of sides. Therefore, h of n is 180 times n minus 2 all over n. That's one quick stop shop in doing all that. You know, I don't read these problems beforehand, so when I do something like this and say, here's how you can do it, I didn't know they were going to ask us about it as well. I was hoping that was all of number 49. That's part A. Part B. Use the function to find h of 9. So h of 9 is now saying find the measure of one interior angle of a regular polygon in a 9-sided shape. So this is substituting it right into here. 9 minus 2 over 9. And this is one of those things where I said you can work things faster this way as well. Yes, it's 180 times 7 over 9, but you can also do 180 over 9 right now. You don't have to multiply. 180 over 9 is 20. So we can do 20 times 7, which is 140. The measure of each interior angle in a nonagon is 140 degrees. Part C. Use the function to find n when h of n equals 150. So h of n equals 150. Now we have to do 150 equals 180 times n minus 2 all over n. This will take a little bit. We got to solve for n, and there's kind of stuff on top and bottom. If I multiply both sides by n, that would be a good jumping point. So times n, top and bottom. Well, times n to get rid of it on the bottom. And you get 150n equals, I'm going to distribute this 180. 180n minus 360. If I subtract 150n to get 30n, add 360, I'll get, divided by 30, you get n equals, I know this, 12. 12 sides. I probably should have used my other formula that I had, 360 over 180 minus 150. I would have gotten it a lot faster. I got that from that other one. D. Plot the points for n equals 3, 4, 5, 6, 7, and 8. What happens to the value of h of n as n gets larger? What do they mean plot? Like on a graph? Well, what we know is as one gets bigger, the other gets bigger, right? Plot the points. Yeah, I guess we need it on some sort of graph. So, okay, well, h of 3 is 180. I mean, you can calculate them. Oh, I'm sorry. Oh, hold on. This is the interior angle measures. I'm sorry. I'm just going to do it kind of fast then. 180 over 3 is 60. H of 4 is 360 over 4, which is 90. So they get bigger, but by a lesser amount. H of 5 is 540 over 5, which is 108. You know, one thing you can do, you don't always have to plug them into the formula, if that makes sense. It's always 180 more than the previous amount. So, you know, like half turns. How many? 7 and 8. So 120. H of 7, I don't know H of 7. I don't know 900 over 7. I think it's a decimal. But I'll round it because they're talking about plotting points. So I want to know what that kind of is. So 900 divided by 7 Yeah, 128.5-ish, 128.6, 128.6 degrees. And h of 8 is, we found this one, or I did, is 135. 1080 over 8, which is 135 degrees. They said plot them. What happens, the value of h of n as n gets larger. We can kind of do a rough plot of that. I'm really not going to get too specific with it because I don't have this thing to scale. But 1, 2, 3, 4, 5, 6, 7, 8. Here's 5. 24, well, I'll do 30s. 30, 60, 90, 120. 30, 60, 90, 120. Here's 3, 60, 4, 90. Check out this curve we're going to have. 5, 108. It's a little more than halfway in between there. 6, 120. Maybe it's a little more than halfway like that. 7, 128 point. I don't think my spacing on these are really good. Let's move that one over a little bit. That one over. No, excuse me. I got to move you over and you over. And maybe I should have done this on a different graph thing. Like that, whatever. 7, that one, 128.5, and 8, that. It gets kind of smaller. It increases, but by a lesser amount. I mean, you could see it in the differences. It increases, but by a lesser amount over time. And yeah, that's what's going to happen, guys. It's going to start converging. Ultimately, listen, you cannot have an interior angle at 180 degrees. It can get larger and larger and closer to 180, but it can't be 180. Otherwise, it can't ever turn in. It'll stay as a straight line. So it approaches 180 degrees as it keeps going. All right, 3 more questions. How do you see it? Is the hexagon a regular hexagon? Explain your reasoning. No. Oh, am I still in black? You see the diagram over there. So the hexagon shown. Let me type it. Good, it's a quick question. The hexagon shown is not a regular hexagon because a regular hexagon would have each exterior angle measure at 360 over 6, which equals 60 degrees. And this varies its angle measures, even if slightly. Some that are 1 degree over, some that are 1 degree less. If they're not all 60, then it's not regular. All angles. It needs to be equilateral and equiangular. I don't even know if it's equilateral. Wouldn't even know based on that. Kind of a weird question. Number 51. Proving a theorem. Write a paragraph. See, they finish with proofs. That's kind of where they go. Write a paragraph proof of the polygon exterior angles theorem. Hint, in a convex n-gon, the sum of the measures of an interior angle and adjacent exterior angle at any vertex is 180. That is very true. Write a paragraph proof of the polygon exterior angles theorem. So let's see. How do I want this? So we can say, let me think of the math version of this, first of all. Why does it keep going to blue? I thought it was in black. Let's think about this. So I is 180 times n minus 2 all divided by n. But E is 180 minus I. Therefore, and I know this isn't a paragraph, but therefore, E is 180 minus 180 times... Oh, this is a sum. I'm sorry. I thought it was the individual angles. Let me do that again. D... D is 180 times n minus 2. That's the sum. I think it's worth doing the i's for that, though. Because the whole thing on the exterior angles is you have to take that thing and multiply. You know what? I think that is worth it. See, did I get rid of it? Okay. E is 180 minus this thing. 180 times n minus 2 over n. But the sum n, if you multiply it by n times e is n times 180 minus 180 times n minus 2 all over n, because this is the sum of all the exterior angle measures. You take each exterior angle of this is a regular polygon. I couldn't care less about that. It's the whole thing is when you get to that part. I don't know if this is working it out. This is definitely not a paragraph. I'm just seeing if I can work this thing out the way I want it to. So that is n times 180 is 180n, and then n divided by n cancels, and that's minus 180 times n minus 2. Let's distribute that. N plus, because negative times negative, 360. Well, 180n minus 180n is 0, and you're left with 360. So n times e equals 360. That's the sum. So sum equals 360 there. So it does work. I don't know how to write a paragraph proof of that. Sum of the measures of an interior angle and an adjacent exterior angle at any vertex 180. So that's kind of what I did there. Listen, I don't know if I can write a paragraph proof for this because I don't know how to say the formula part for that. I'm not going to write these 180 minus all the time. But here's what I did. I'm going to say it out loud. I took how you find an interior angle measure of a regular polygon. It's kind of working it out that way. I wonder if there's anything else I can do based off that. But E is the supplement of that. They even tell you themselves that it's an adjacent exterior angle, and that's the thing. So E is a supplement of that right here. So when I subtract that amount out, then I have the measure of any one exterior angle in a regular polygon. But if I multiply by the number of sides on both sides of this thing and distribute that into it, it cancels out that n. It kind of just works some things out. You end up getting 360. That's the sum. It always adds to 360. I don't know. I didn't write the paragraph one. I feel like I maybe should have, but I don't know what else to say. The calculations speak for themselves. They shouldn't have said paragraph proof. They just said prove it. All right, number 52, last question. Abstract reasoning. You're given a convex polygon. You are asked to draw a new polygon by increasing the sum of the interior angle measures by 540 degrees. How many more sides does your new polygon have? Explain your reasoning. So so 3. It's 3 more sides. So each polygon, I'm going to just write it. Each polygon, each triangle, new triangle is 180 degrees. Yes, draw a new polygon, increase in the sum of triangle. So each new triangle is 180 degrees, and 540 over 180 is 3. It's kind of like every time you add another 180 degrees, that's a whole nother side added. See, if I had a triangle, this one ended up looking really good, but if I had a triangle and I added another triangle to this, like this, boom, boom, I now have instead of a 3-sided shape, I now have a 1, 2, 3, 4-sided shape. If I add another triangle, I'll have a 1, 2, 3, 4, 5-sided shape because one side gets covered and a new side replaces that old side that was there. The only true new side is this one. This is a new side, but it replaced this, and this side got dropped. So check this out. See this side right here? It's about to be replaced by this, and this side goes away, replaced by it. So no change, and then this is another one. So this is 1, 2, 3, 4, 5, 6 sides. Although I've added, remember what was a triangle? I added 180, 360, 540 degrees from a 3-sided shape to a 6-sided shape. That's just a look at it. That's the last question there. All right, guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Later, we'll see something on section 7.2 where we really start dealing into the nitty-gritty of different types of quadrilaterals. A bunch of properties to be had, a bunch of math we can do with them, I'm sure. I'm not sure how the textbook's going to do them, but I've seen that stuff in the past. We're probably going to look at it. So thanks for watching. Check out the timestamps and PDFs and stuff down below and the IM2 playlist if you want to find more from me. Thank you. Take care. Have a great one.